So we want to start talking about a new chapter, statistics. And in this section, we'll talk about visual displays of data. We'll mention a histogram, frequency polygon, a line graph, bar graph. We'll also talk about circle graphs and stem and leaf plots, and frequency distribution and grouped frequency distribution. So we'll talk about all of these things in this section. A lot of this material you may already be familiar with, but you just need the definitions. To get started, I looked up a definition of statistics. Two different options. They really mean very much the same thing for us. A branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. And the second definition is a collection of quantitative data, which means numerical data. So that's what we're going to be working with. A lot of ideas in statistics you may very well be aware of. Now, statisticus is where the word statistics comes from, and that's Latin, and it means of the state. And you would think it has nothing to do with that, but if you think about the government, that's probably one of the first institutions that might use statistics. And so it's information the government was collecting, and it's this data that could become important to making decisions. So probably the government used statistics first, but again, it comes from the Latin word statisticus. Now, when you talk about population, the word population includes all items of interest. So it's kind of like the universal set. So when you're talking about the population of something, when you're talking about data, that's the whole set that you're talking about, are all items of interest. Whereas a sample includes some, but not ordinarily all the items of interest. And a good example of that is if you think about an election. And before the election occurs, you have these polling groups that take a sample of the population to determine maybe an outcome of the election, to predict the election. And so that would always use a sample, whereas, the population of the United States is many millions of people. A sample might include, say, 2,000 people, and to see what their opinion is, and that may very well represent the feelings of the entire United States, but you can't poll everybody, so often a sample is what is needed. And main areas of the study of statistics, they divide it up into two things. Number one, descriptive statistics consist of collecting, organizing, summarizing, and presenting data or information, in short, describing the data. These descriptions can apply to populations or to samples of populations. Then you have inferential statistics, and that consists of drawing conclusions about populations on the basis of information from samples taken from those populations. So again, back to those polls, they do some descriptive statistics and say, out of this many people polled, this many said they were going to vote for this particular candidate, and the rest said they would vote for this particular candidate. But then they could use that information to infer which candidate might win the election. So that's a basic idea of what we mean by inferential statistics, what to expect in the future because of certain data. So for our first example, I just want you to consider a population of 10,000 colored beads in a bowl. So a bunch of beads in a bowl. It says 3,000 of these beads are green. They want us to use this information in probability theory to make predictions and samples about samples of beads drawn from the bowl. So that really should be about samples of beads drawn from the bowl. And here we have our 10,000 beads. Is that like 10,000 beads in that bowl? It looks a little bit blurry to me, but we're going to assume that 3,000 of those beads are green. Somebody counted every single one of them. Now, how many green beads should we expect if we select a random sample of 25 beads? How could we handle this? Okay, so let's think about this. If they want us to guess out of 25 beads how many of them would be green, well, what we probably should do is figure out the percentage of green beads in the bowl. So the percentage of green beads, we would do 3,000 divided by 10,000 Now, if you divide that in your calculator, that's going to give you 0.3 or 0.30 if you like that better. Now, that's 30%. So 30% of the beads in the bowl are green. That's the way they set this up for us. Now, if we were to draw out 25, then we would expect that 30% of those beads be green. So how do we calculate that? Well, we take our 30%, which in decimal form is 0.30, multiply that by 25, and that gives us 7.5. Now, you can't have 7.5 beads, so my guess that would be, say, 7 or 8 beads. Right? So 7 or 8 beads is what we should expect. Around about, again, we got 7.5. Does that mean it might be 9 or 10? Yeah, it might be 9 or 10, right? The 30%, again, is an exact value of the population. 30% are green. But when you take a symbol, it's probably close, but maybe not exact. Let's find out. If we really take a sample of 25 beads, look there. There's our sample of 25 beads. Now, when you take a look at this, and by the way, this calculation that's up above here is just the typed up version of what we just did. So let's actually count the green beads. Now, if you'll notice, the green beads are a little bit hard to discern from the blue beads, but I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So there were 9 green beads here. So our 7 or 8 guess is pretty close. It's not exact, but it's pretty close. Now, if we did not know the number of green beads in the population of 3,000 beads, how could we use the sample to predict the number of green beads in the population? So this is backwards. What if we have the sample, but we didn't actually have the count of the 10,000? So this is more like a population, and you're polling, a group of people to get the ideas of the mass of people. So we're working backwards. So it says the sample right here in green shows 9 green beads, which is 9 out of 25, right? So we counted them. We said there were 9. If you divide that by 25, that's going to give you 36%. That would be the guess of what would be in our population. So we would calculate 36%, so 0.36. I got to get my pen working first, though. All right, so how about 0.36 times the population, which is 10,000, and y'all know 36% of 10,000 would be 3,600 green beads. So we did a couple of things here. We used our original percentage to estimate what the sample might be, and we were off just a little bit, and then we did it backwards. We took a sample to estimate what the original percentage of green beads would be. And notice we estimated more. We've got 3,600 when there's actually 3,000 in the bowl. Now, what do you think would make a better sample? We sampled 25 beads. What do you think would be closer to our percentage? How about if we sampled more green beads? More beads, not more green beads. We want to know how many of those are green, right? So what if we picked a sample of 50 or even 100? Would that not make a better sample to estimate the original population? Let's find out. All right, so question B, consider the sample of 100 beads from the population. Now, we decided 100 or 50, anything more than 25 might give us a better sample to estimate the original population. What does this sample reveal about the percentage of green beads in the original population? Now, instead of counting them this time, again, it's hard to tell the difference between the blue and the green beads. There are 28 green beads. You'll have to just trust me or pause me and count them yourself. Again, some of these, like this bottom row, what I'm circling right here, if you can tell, the third one on the bottom is blue. This one right here is blue, so it's really hard to discern the green from the blue, but there are 28 green beads, okay? Well, that would be 28 out of 100, which is 0.28, right? If I change that to a percent, that's 28%. Matter of fact, the definition of percent means out of 100. So if you have 28 over 100, you know that's 28%. Now, how would we estimate the population for this. Now, we know there's 3,000 in the population, but we're assuming we don't know this. And we're trying to see if this gives us a good estimate. So if I take 0.28, or 28% of 10,000, that's the total beads in the bowl, then you would get 2,800 green beads. Now, is that a good estimate? I'd say it's not bad. You know, it's 3,000 were in there, and we estimated from our sample here that we would have 2,800. So remember when we did 25, we had an overestimate of 3,600, but when we pulled out 100 beads, we get an underestimate of 2,800. But I would say that's closer than the 3,600. And if we could even estimate 200 or 300, we would get closer and closer to that 30% of green beads in the actual population. So this is to show you can use a sample space to estimate the statistics for a real population if needed. So continue with a couple of more definitions. Raw data is information that has been collected and not yet organized or processed. So you're just counting the information, but you haven't organized it at all or done any kind of processing with the information. And raw data can be broken down into either quantitative, which is numerical, or qualitative, which is non-numerical. But sometimes your data is not numerical at all. Again, we call that qualitative data. Now, here's some examples of raw data. Quantitative data, for instance, the number of siblings in 10 different families. You know, so we're counting siblings, so one family might have 3 siblings, another family 1 sibling, another family 2 siblings. Whereas qualitative data is the makes of 6 different automobiles. Okay, so you got Toyota, Ford, Kia, Toyota, Chevrolet, Honda. So that says something about the information, but you're not counting Toyotas or counting Fords. You're just saying the makes of 6 different automobiles. Okay? Now, the bottom here is a point about quantitative data. You remember numerical data. Quantitative data are generally more useful when they are ranked or arranged in numerical order. I think you'll find it beneficial, if possible, whenever you're working with raw data, just to put it in order from smallest to largest typically, but you could put it the other way around if needed. You're almost always going to want to do that, especially to calculate certain things about the data. Okay, so for our first official, I say formal example for this section about visual displays of data, we've got 25 members of a psychology class were polled about the number of siblings in their individual families. Construct a frequency distribution and a relative frequency distribution for their responses, which are shown here. So this is something that you'll need to do with data. And to do this, well, let me go ahead and tell you, you're going to need a table. And in your table, you're going to need headings of the number X. So what I'm going to put in this column are the numbers that are up here. So notice we have numbers of, hold on, let me get rid of this. Oh, there it went. We have numbers of 2, 3, 1, 3, 3, 5, 2, 3. What I want you to do is take a look at all the different numbers. What numbers do we have? And what these numbers are saying is, one person said there were 2 siblings in her family. Another person said there were 3 siblings in, say, his family. Another person only had 1 sibling. You see what I mean? Then there were 3, then there were 3, and they just listed what all the people in the psychology class stated. So we're going to have a column here for our numbers. Now, the frequency means how many times did this number show up. And then here's the good part, the relative frequency. And for the relative frequency, you take the number of times it showed up divided by the total of your numbers. Okay? How many people were polled. And notice it says 25 members. Okay? So, here we go. Let's do this ourselves. So first, let's take a look at our data, right? So what numbers do we have listed? There's definitely a 1 in the group. Notice there's not a 0. And I asked myself, what did they really mean by this? When they say siblings in the family, are they talking about, You know, if you're an only child, you have 0 siblings, right? But I think they mean how many kids are in the family. So 1 would mean there's 1 child, 2 would mean there's 2 children. But honestly, it doesn't matter to do this problem, so don't get hung up with that. There is a 1 listed, so I'm going to put 1 in this first column. There's a 2 listed. There's definitely a 3. Do you see a 4? I do. Do you see a 5? I do. Do you see a 6? I do. Do you see a 7? And so notice if you scan through, you don't see a 7. That's why I conveniently picked this many rows. You notice there's not a row for 7 because I counted already. Now frequency. This is where things can get a little bit sticky and it's easy to miscount, so be careful. So I'm going to go through and count my 1. So that's 1, 2, 3, and then 4. I'm seeing 4 ones. Now I have a way to check ourselves in the end. So just hang with me. Let's go ahead and count the 2s. Or matter of fact, you just pause me and fast forward it and see if we get the same count. So when I count 2s, I see 1, 2, 3, 4, 5, 6, 7. Okay, I'm going to count 3s now. 1, 2, 3, 4, 5, 6. Just see 6 of those. 4s. 1, 2, 3. And that's all I see. 5s. 1, 2, 3. I see 3 5s, and I'm on to the 6s. And I'm scanning through, and I'm scanning through. There's a 6, and there's a 6, and I see 2 of those. Now, to check myself, I think it's a good idea to add these together. What should it add to be? 25, right? So your frequency should add up to how many values of data you have, or we did something wrong. So 4 and 7 is 11, and 6 is 17, and 3 is 20, and 3 is 23. Yes, that does add to 25. Check. Now, how do you find relative frequency? You take your frequency 4 and divide it by 25. And 4 divided by 25 is 0.16, which is 16%. Now, the 16% is what I'm interested in, okay? Then I take 7 and divide that by 25, okay? 7 divided by 25 gives me 0.28, which is 28%. So you see what to do. 6 divided by 25. 6 divided by 25 gives me 0.24, which is 24%. 3 divided by 25 is 12%, or 0.12, which is 12%. Notice these next two relative frequencies are 12%. And then the last one, 2 divided by 25, gives me 0.08. Notice when to change it to 100%, I'm moving that decimal 2 places to the right, which gives me 8%. Now my question to you is, what should this percentage total to be? 100%, right? Everything. These are like probabilities right here. 0.1628, 0.24, 0.12, 0.12, 0.08, which is really 1600s, 2800s. You see what I'm saying? But when you change them to percent, it adds to 100%. When you leave it as a probability, okay, or a regular relative frequency without changing it to a percent, it should add to 1, because 100% is 1. So I'm checking. And 16 plus 28 plus 24 plus 12 plus 12 plus 8 does add to be 100%. So listen, I really encourage you to check these. Your frequency should add to be how many people were polled, or whatever your data is, the total number of data points, and your relative frequency should add up to be 100%. Now on this page, I have the table typed up for you so you could see it a little bit neater, and I can make it a little smaller so I can put more information on this page. I want to show you something from this given information. If you'll notice at the top right, I have a histogram for you. That's what this is called. Notice that here's a definition. You want to write this down. A histogram is a series of rectangles whose lengths represent frequencies are placed next to one another. Notice how they're touching, which is slightly different than a bar graph we'll have coming up shortly. But a histogram, the rectangles are touching. Notice for a frequency of 1, the first the first rectangle we have going on, look at the height is 4. So that's frequency on the left. Across the bottom is the number of siblings. So for a frequency of 2, for siblings of 2, that showed up 7 times. So that rectangle, notice how it goes up to 7. For 3 siblings, the frequency was 6. For 4 siblings and 5 siblings, the frequency was 3. Notice how they're the same height. And for 6 siblings, the frequency was just 2. Now, why is this a value? Well, you can quickly look at this and see that 2 siblings is the highest. And I still want to say that probably means 2 children in the family. And that shows up the most. That's the most frequent. And then 3 is the next, and then 1 is the next, and then 4 and 5 and 6 falls below. So when you have this visual representation of data, you can look at it quickly and come up with that. Whereas you have a chart like this, you can dig through and say, oh, look, 7 shows up more than the rest of them. So 2 is the most common number of siblings in a family. But when you look at it in this visual data style, you can see it a little better. Something else we could do is called a frequency polygon. Again, definition to the left. Frequency polygon is you plot the frequency as a single point. So notice, again, for 1, you plot 4 because 1, the frequency was 4. 2, you make a dot at 7. 3, you make a dot at 6. So these are individual dots, and then what do? You connect the dots. Notice at the ends, though, and this is something different about a frequency polygon versus, say, a line graph we'll talk about soon, is that before the information starts at 1, it drops off at the bottom. It just makes a complete polygon out of it instead of leaving this as an open space and just starting at 4, which I think is a little strange. But the point is, again, you can look at it and easily tell that 2 is the most common answer because it's the highest point on that polygon. Now, sometimes there's a large amount of data such that a basic frequency distribution is not reasonable. In this case, the data can be grouped into categories to create a grouped frequency distribution. So sometimes you can't just list it like we did, and you'll see what I mean with an example. We're going to try a grouped frequency distribution, but before I do that, let me give you some guidelines. All right, number 1, make sure each data item will fit into one and only one class. So when we divide up our large amount of data into groups or classes, your answer can only fit in one category. You can't say, well, this fits over here and it fits over here, because then you'd have to decide where it fits, and that would skew the data. Okay. Number 2, try to make all classes the same width. That's not always possible, but it's something you should try to do. Number 3, make sure the classes do not overlap. This is so important. You don't want to make a range that goes from, say, or a class that goes from 50 to 65, and then the next class goes from 60 to 75. Do you see what I mean? They overlap. You can't do that. You do not want to do that. Number 4, use from 5 to 12 classes. If you have too few groups or classes, it's hard to see what's going on with the data, and if you have too many, it's really hard to see what's going on with the data. So try to pick between 5 and 12, but also you want to do what's convenient about the data as well. So in example 2, this is exactly what we're going to do. We're going to construct a histogram and a frequency polygon, but before we do that, we need to group this and do a grouped frequency distribution. So 40 students selected randomly in the school cafeteria one morning were asked to estimate the number of hours they had spent studying in the past week, including both in-class and out-of-class times. Their responses are recorded here. So we've got somebody that studied 18 hours in a week, somebody that studied 60 hours in a week, somebody that studied 72 hours. You see where we're going with this. It says tabulate a grouped frequency distribution. So again, notice grouped frequency is going to have classes. So anytime you're asked to do a grouped frequency distribution, you're going to have to divide this up into classes, and you're going to want to. Look at all this information. We don't want to count 18 and figure out how many 18 show up, and then 60 and figure out how many 60 show up. We want to group these things together. After we do this, we're going to construct a histogram and a frequency polygon to represent the data. Whew, now, things we need to look for, and you may even want to put these in numerical order. Sometimes that takes a while, but from smallest to largest. But let's see if we can find the largest number in the group and the smallest number in the group, and that's going to help us pick our classes, right? So I'm looking for the largest first. Why? Just because I don't know. I just am. So I'm scanning 18. There's a 60. 72 seems to be the largest. 58, 33, 15. I'm just looking at all these to see if I can find any number larger than 72. Because I saw 72 on that top row. And I do not see anything yet. No. So it looks like 72 is the largest. So I'm going to write that down. So our largest is 72. You be looking for the smallest. Okay, the smallest number on this list. I have 18. There's a 15. There's a 12. So right now 12 is the smallest. There's a 14, but we still have 12 small. Okay, 12 is the smallest. Now, if I say largest minus smallest, so 72 minus 12, that gives me 60. Okay, now if I'm trying to take 60, let's just say 60. Remember the rule is there needs to be between 5 and 12 classes. You could just divide that by 5, and the step would be 12. Each class would be 12 large. So we could start at 12 and then add 12 and go to 24, and then we have a class from, say, 24 to 36, and then 36 to 48. You see, I'm just adding 12. But you know what? What if we did classes of just the 10s, and then 20s, and then 30s, and then 40s, and then 50s? I think that would be more convenient. You see what I'm saying? So it wouldn't be wrong to have each class as 12, but it's really going to be easy to see the data if we just grouped all of our teens together and all of our 20s together. You with me? So if we do that, look, this is what it would look like if I just save you a minute. And there's our class limit. So we're going to take a look between 10 and 19. How many do we have? Between 20 and 29, how many do we have? See where I'm going with this? 30 to 39, 40 to 49, 50 to 59. Let's start counting and so you can see. So I'm going to try to highlight these. So there's an 18, a 15, a 12, a 16. Highlighter comes in handy, don't you think? And I'm looking, there's a 14 and a 17. Trying to see if there's any other teens that pop out. And if not, my frequency is 1, 2, 3, 4, 5, 6. So I'm seeing 6 between 10 and 19. So what do? I just put my tally is 6 between 10 and 19. Oh, here's what they mean by tally. 6 is my frequency. Here's what they're doing. Let me show you. The tally comes in handy. So 18 goes here. Let's do it this way. 60 fits in the 60s. 72 fits in the 70s. A 58 fits in the 50s. 33 fits in the 30s. 15 fits in the teens again. 12 fits in the teens. 36 fits in the 30s. I like this method. 16 fits in the teens. 29 fits in the 20s. 26 fits in the 20s. 41 fits in the 40s. Are you getting tired of this? 45 fits in the 40s. 25 fits in the 20s. 32 fits in the 30s. 24 fits in the 20s. 22 fits in the 20s. 1, 2, 3. Here's what I was trying to do, trying to get to 5. You know, when you do 5, you can do this. And it makes it easy. Now, I know that gets old. I know you're capable of doing that. I like the tally method. Or if you had a highlighter like I did, you could do just the counting method and count one at a time. I think you'll make less mistakes if you do the tally method. Okay, now I've already summed up this information for you, so let me flip to that page. Look, here it is. So I did count the 6 right. That's good news. And it's all tallied up. The frequency, you see here how many times they showed up, and even the relative frequency. So where did they get this 6 divided by 40? Remember, 6 is the frequency, And there were 40 students. It even says it right there, 40 students that were polled. So all of these are divided by 40. Now remember what we could check? Things we could check is 6 plus 9 plus 12 plus 6 plus 4 plus 2 plus 1. That better equal to 40. And then if you add 15 plus 22.5 plus 30 plus 15 plus 10 plus 5 plus 2.5, that should add to what? 100%, right? So this should always add to 100%. There is a possibility due to rounding you could be off just a little bit, but normally, even with rounding, it's going to work out to 100%. So check those two things before you do anything. Now what I'm supposed to do is create a histogram for this. Now you could draw this for yourself without a doubt. So when you draw a histogram, okay, so you need a vertical line and a horizontal line. And you're going to draw how many rectangles? Well, one for each class. 1, 2, 3, 4, 5, 6, 7 rectangles. Okay. Now the first rectangle from 10 to 19, you would label that at the bottom. So 10 to 19, we have a rectangle that goes up to 6. Now when you do this, you might want to put a scale to the side. Look, 12's our highest. So I need to go up to 12. So let's say that's 2, 4, 6, 8, 10, 12. So when I go up to 6 and draw my first rectangle, there was 6 right there, there's 12. So I draw up to 6 and then down. And then for my next rectangle is between 20 and 29. Now my problem is going to get the label at the bottom. 20 to 29 was 9. So that's 8. And then right there is 9. There's my next rectangle. They're supposed to be connected to each other. And then the next one is 30 to 39. And then I draw my rectangle and it went up to 12. So I go up to 12. You see how we're doing this. And so I'm not making mine really pretty right now, but you could take your time and use a ruler and divide this out at the bottom where it looks very nice. But if you do that, you'll get something that looks very similar to this frequency distribution. Okay. Notice how they put their numbers on the side. That would have helped me a whole lot, right? Because writing my classes or my ranges down here at the bottom is what took up so much space. So if I write them vertically like this, then my rectangles will line up on top of it. Notice they didn't put as many values over here for measurement. I like that I had 2, 4, 6, 8, 10, 12. It's a little easier to see how high they go. But you know what? We can clearly see that between 30 and 39 is what most students study. When you look at information like this, it's a little bit harder to see. You see the biggest frequency is 12. You see 30% is the biggest percentage over here. But you really get a good feel for it when you see it in this histogram form. Well, what about drawing your own polygon, right? Frequency polygon. So again, I tried to pick the black pen, but it just didn't let me. Here we go. So here we go. And again, you would need to put these classes along the bottom, right? Okay, and then 2, 4, 6, 8, 10, 12 is the way I'm doing it. And so for our first class, 10 to 19, trying to write like sideways without flipping it around, 10 to 19, then it's 6, so I plot my point at 6. And then my next class is 9, so I plot my point at 9. Remember, this is 10 and this is 12, so 9 would be about there. My next class, I plot at 12 up here. My next class is at 6. My next drops down to 4. And I have points disappearing, you see. And you connect the dots. So I connect with straight line segments. Don't make it curvy, although my wiggly screen makes it curvy. Now this one, to make a polygon, see, this is a line graph that we have going. But to make that frequency polygon, they just come down to the bottom at the end one. And then over here on the far right, where we had 7 to 79, and there was just a count of 1, and it's connected, then you would come down here as well. Now mine's not complete. I left some values out because I wanted to show you a good looking one. And there's a good looking one. Okay, so see how these ends come straight down? Right here at the end. Just doesn't let me select my pen. So there and there at the end, it just comes down to the graph. It kind of tapers down and then touches, and that's what makes a grouped frequency polygon. So you got this, right? It's all about definitions. You just need to know the definitions of these things. So when it asks you to do calculate relative frequency, you know what to do. Grouped relative frequency is what we did here. A histogram is with the bars and the rectangles touch each other. And a frequency polygon, you just plot each of the points separately, connect them with straight lines, and at the ends come down to like the x-axis.